Hello friends, in this session we will discuss on sustainable development and environmental accounting. Let us begin with the introduction. In order to identify the environmental problems and to choose appropriate remedy to cure it, we need to take into consideration the time dimension. The static efficiency allows us to evaluate those circumstances where time is not crucial aspect of the allocation problem. For example, allocating resources such as water or solar energy where next year's flow is independent of this year's choices. But if we take into account more complicated criterion, dynamic efficiency, it is suitable for those circumstances where time element is crucial aspect. For example, combustion of deflectable resource such as oil, since supplies used now are unavailable for future generations. There are three important benefits of following the criterion of time dimension. Number 1, this criterion is useful in identifying environmental problems and referring out their behavioral sources. Number 2, it is providing a basis for identifying types of remedies. Number 3, it is helping in designing the various policy instruments that can be used to restore some sense of balance. Though the aforesaid criteria are useful to attain harmony between the economy and the environment, but in a general sense, the efficiency criteria are designed to prevent wasteful use of environmental and natural resources. They care only the value of environment, that is, the size of the pie and not the distribution of the pie. That is what shared value goes to all recipients. In other words, fairness or justice concerns should accompany efficiency considerations. In this module, our concern is fairness, the treatment of future generations. We begin by considering a specific ethically challenging situation, the allocation of a delectable resource over time. Using a numerical example, we shall trace out the temporal allocation of a depletable resource using the dynamic efficiency criterion and show how the allocation is affected by changes in the discount rate. To lay the groundwork for our evaluation of fairness, we then turn to the task of defining what we mean by intertemporal fairness. Finally, we consider not only how this theoretical definition can be made operationally measurable, but also how it relates to dynamic efficiency. To what degree is dynamic efficiency compatible with intergenerational fairness? A two-period model. Dynamic efficiency balances present and future uses of a depletable resource by maximizing the present value of the net benefits derived from its uses. This implies a particular allocation of the resource across time. We can investigate the properties of this allocation and the influence of such key parameters as the discount rate with the aid of a simple numerical example. We begin with the simplest of models deriving the dynamic efficient allocation across two time periods. Assume that we have a fixed supply of a depletable resource to allocate between two periods. Assume further the demand function is constant in the two periods. The marginal willingness to pay is given by the formula P is equal to 8 minus 0.49 and the marginal cost is constant at $2 per unit as shown in this figure. Note that if the total supply was 30 or greater and we were concerned only with these two periods, an efficient allocation would produce 15 units in each period regardless of the discount rate. 30 units would be sufficient to cover the demand in both periods, the consumption in period 1 does not reduce the consumption in period 2. In this case, the static efficiency criterion is sufficient because the allocations are not interdependent. Let us examine the case when the available supply is less than 30, say it is equal to 20. The question is that how do we determine that efficient allocation? According to the dynamic efficiency criterion, the efficient allocation is the one that maximizes the present value of the net benefit. The present value of net benefit for both periods is simply the sum of the present values in each of the two periods. To take a concrete example, consider the present value of a particular allocation, 15 units in the first period and 5 in the second. The dynamically efficient allocation of this resource has to satisfy the condition that the present value of the marginal net benefit from the last unit in period 1 equals the present value of the marginal net benefit in period 2. Even without mathematics, this principle is easy to understand, as can be demonstrated with the use of a simple graphical representation of the two-period allocation problem. The figure depicts the present value of the marginal net benefit for each of the two periods. The net benefit curve for period 1 is to be read from left to right. The net benefit curve intersects the vertical axis at $6, demand would be 0 at $8 and the marginal cost is $2. So, the difference marginal net benefit is $6. The marginal net benefit for the first period goes to 0 at 15 units because at that quantity the willingness to pay for that unit exactly equals its cost. The only challenging aspect of drawing the graph involves constructing the curve for the present value of net benefits in period 2. Two aspects are worth noting. First, the 0 axis for the period 2 net benefits is on the right rather than the left side. Therefore, increases in period 2 are recorded from right to left. This way, all points along the horizontal axis yields a total of 20 units allocated between the two periods. Any point on that axis picks a unique allocation between the two periods. Note that the sum of the two allocation in figure is always 20. The left hand axis represents an allocation of all 20 units to periods 2 and the right hand axis represents an allocation entirely to period 1. Second, the present value of the marginal benefit curve for period 2 intersects the vertical axis at a different point than does the comparable curve in period 1. Why? This intersection is lower because the marginal benefits in the second period need to be discounted, multiplies by 1 over 1 plus r to convert them into present value from since they occur 1 year later. This with the 10% discount rate, we are using the marginal net benefit is $6 and the present value is 6 upon 1.10 US dollar is equal to $5.45 US. Note that larger discount rates would rotate the period 2 marginal benefit curve around the point of 0, net benefit Q is equal to 5, Q2 is equal to 15 toward the right hand axis. The efficiency criteria are equally appropriate for evaluating resource allocations generated by markets, government rationing, or even the whims of a dictator. When we deal with any efficient allocation method, we must take into account the scarcity. Intertemporal scarcity imposes an opportunity cost that here we refer to as the marginal user cost. When resources are scarce, greater current use diminishes future opportunities. The marginal user cost is the present value of these foregone opportunities at the margin. Using more resources in present out of given leaves less for the future, and that is the opportunity cost of using more resource in the present. If this opportunity cost is high, then it leads to inefficiency in the sense that the cost is imposed on future. This additional marginal value created by scarcity is the marginal user cost. We can make this concept even more concrete by considering its use in a market context. An efficient market would have to consider not only the marginal cost of extraction for this resource, but also the marginal user cost. Whereas in the absence of scarcity, the price would only the marginal cost of extraction. With scarcity, the price would equal the sum of marginal extraction cost and marginal user cost. In an efficient market, the marginal user cost for each period is the difference between the price and the marginal cost of extraction. Defining intertemporal fairness. While no generally accepted standards of fairness or justice exist, some have more prominent support than others. One such standard concerns the treatment of future generations. What legacy should earlier generations leave to later ones? This is particularly difficult issue because in contrast to other groups for which we may want to ensure fair treatment, future generations cannot articulate their wishes, much less negotiate with current generations. One starting point for intergenerational equity is provided by philosopher John Rawls in his monumental work A Theory of Justice. Rawls suggests one way to derive general principles of justice is to place hypothetically all people into an original position behind a veil of ignorance. This veil of ignorance would prevent them from knowing their eventual position in society. Once behind this veil, people would decide on rules to govern the society that they would, after the decision, be forced to inhabit. In our context, this approach would suggest a hypothetical meeting of all members of present and future generations to decide on rules for allocating resources among generations. Because these members are prevented by the veil ignorance from knowing the generation to which they will belong, they will not be excessively conservationist or excessively exploitative. What kind of rule would emerge from such a meeting? One possibility is the sustainability criterion. The sustainability criterion suggests that at a minimum future generations should be left to no worse off than current generations. Allocations that impoverish future generations in order to enrich current generations are, according to this criterion, patently unfair. In essence, the sustainability criterion suggests that earlier generations are at liberty to use resources that would thereby be denied to future generations as long as the well-being of future generations remains just as high as that of all previous generations. On the other hand, diverting resources from future use would violate the sustainability criterion if it reduced the well-being of future generations below the level enjoyed by preceding generations. One of the implications of this definition of sustainability is that it is possible for the current generation to use resources as long as the interest of future generations could be protected. Do our institutions provide adequate protection for future generations? We begin with examining the conditions under which efficient allocations satisfy the sustainability criterion. Are all efficient allocations sustainable? Are efficient allocations fair? There is no surety that efficient allocation satisfies sustainable criterion. Even in our example of 2 periods, more resources are allocated to the first period than to the second. Therefore, new benefits in the second period are lower than in the first. Sustainability does not allow earlier generations to profit at the expense of later generations. If the allocation is dynamically efficient, it will always be possible to set aside sufficient net benefits accrued in the first period for those in the second period, so that those in the second period will be at least as well off as they would have been with any other extraction profile. If you believe that setting aside half of the available resource for each period would be a better allocation than the dynamic efficient allocation. If the dynamic efficient allocation is to satisfy sustainability criterion, we must be able to show that it can produce an outcome such that each generation would be at least as well off as it would be with the equal allocation. The benefits in one period must be shared with the other, general for maintaining sustainability. Hence, the sharing between the periods should take place. If there is no sharing between the periods, then the sustainability criterion is violated and the second generation is worse off. In the dynamic efficient allocation, the first generation may have net benefits marginally greater than the second generation. But if there is sharing and the first generation can save its excess that yields every year some return, and if the return is transformed to second generation by means of sharing, then the second generation would be better off. This can happen in the dynamic efficient allocation with sharing. If the second generation had demanded that resources be allocated equally between the 2 periods, then it would have been deprived of the benefits. This is an advantage of dynamic efficient allocation with sharing. However, we must note that the required degree of sharing must take place. Applying the sustainability criterion. One of the difficulties in assessing the fairness of intertemporal allocations using this version of the sustainability criterion, that is dynamic efficient allocation, is that it is so difficult to apply. Discovering whether the well-being of future generations is lower than that of current generations requires us not only to know something about the allocation of resources over time, but also to know something about the preferences of future generations. That is a tall order. However, we can rely on a version of the sustainability criterion that is more operational. Hartwig rule, an operational criterion of sustainability. John Hartwig in 1977 demonstrated a constant level of consumption would be maintained perpetually from an environmental endowment if all the scarcity rent derived from resources extracted from that endowment were invested in capital. That level of investment would be sufficient to assure that the value of the total capital stock would not decline. 2 important insights flow from this reinterpretation of the sustainability criterion. Number 1, with this version, it is possible to judge the sustainability of an allocation by examining whether or not the value of the total capital stock is non-declining. That test can be performed each year without knowing anything about future allocations or preferences. Number 2, this analysis suggests the specific degree of sharing that would be necessary to produce a sustainable outcome, namely all scarcity rent must be invested. Let us try to understand this with an analogy. Suppose a grandparent left you an inheritance of 10,000 US dollar and you put it in a bank on which you earn 10% interest. The appropriate choice could be to spend 1000 US dollar, that is an interest per year, and kept the principal amount intact that would last forever. If you spend more than 1000 US dollar per year, the principal amount would necessarily decline over time and eventually the balance in the bank go to zero. In the context of this discussion, spending 1000 US dollar per year or less would satisfy the sustainability criterion, which spending more would violate it. In this respect, Hartwig rule suggests that one way to tell whether an allocation spending pattern is sustainable or not is to examine what is happening to the value of the principal over time. If the principal is declining, the allocation, that is spending pattern, is not sustainable. If the principal is increasing or remaining constant, the allocation is sustainable. Let us see the application of this logic to environment. In general, the Hartwig rule suggests that the current generation has been given an endowment. Part of the endowment consists of environmental and natural resources known as natural capital and physical capital such as building, equipment, school and roads. Sustainable use of this endowment implies that we should keep the principal, that is the value of endowment, intact and leave off only the flow of services provided. We should not, in other words, chop down all the trees and up all the oil, leaving future generation deprived of resources. Rather, we need to assure that the value of the total capital stock is maintained, not depleted. The desirability of this version of the sustainability criterion depends crucially on how substitutable the two forms of capital are. If physical capital can readily substitute for natural capital, then maintaining the value of the sum of the two is sufficient. If, however, physical capital cannot completely substitute for natural capital, investments in physical capital alone may not be enough to assure sustainability. The assumption of complete substitutability between physical and natural capital is untenable for certain categories of environmental resources. Although the substitution is tenable, for example, between the air and universal air conditioning, but the expense and the artificiality of this approach make it an absurd compensation. Hence, the interrogational compensation must be approached carefully. Recognizing the weakness of the constant total capital definition in the face of limited substitution possibilities has led some economists to propose a new definition. According to this new definition, an allocation is sustainable if it maintains the value of the stock of natural capital. This definition assumes that it is natural capital that drives future well-being and further assumes that little or no substitution between physical and natural capital is possible. To differentiate these two definitions, the maintenance of the value of total capital is known as the weak sustainability definition, while maintaining the value of natural capital is known as the strong sustainability definition. A final definition, known as environmental sustainability, requires that certain physical flows of certain key individual resources be maintained. This definition suggests that it is not sufficient to maintain the value of an aggregate. For a fishery, for example, this definition would require catch levels that did not exceed the growth of the biomass for the fishery. For a wetland, it would require the preservation of the specific ecological functions. Implications for environmental policy. In order to be useful guides to policy, our sustainability and efficiency criteria must be neither synonymous nor incompatible. These differences have policy implications. In fact, they suggest a specific strategy for policy. Among the possible uses for resources that fulfill the sustainability criterion, we choose the one that maximizes either dynamic or static efficiency as appropriate. However, the sustainability criterion itself is insufficient because it fails to provide any guidance on which of the infinite number of sustainable allocation should be chosen. That is where efficiency comes in. This combination of efficiency with sustainability turns out to be very helpful in guiding policy. Many unsustainable allocations are the result of inefficient behavior. Correcting the inefficiency can either restore sustainability or move the economy a long way in that direction. Correcting inefficiencies can frequently produce win-win situations. In win-win situations, the various parties affected by the change can all be made better off after the change than before. This contrasts sharply with changes in which gains to gainers are smaller than the losses to the losers. Win-win situations are possible because moving from inefficient to an efficient allocation increases the net benefits. The increase in net benefits provides a means for compensating those who might otherwise lose from the change. Compensating losers reduces the opposition to change, thereby making change more likely. Summary: both efficiency and ethical considerations can guide the desirability of private and social choices involving the environment. The former deals with the eliminating waste in the use of resources, and the latter is concerned with assuring the fair treatment of all parties. Sustainable development is based upon the notion that the present generations should be free to pursue their own well-being without demising the welfare of future generations. This notion gives rise to three alternative definitions of sustainable allocations. Number one, weak sustainability. It implies that the resource used by present generations for their well-being should not prevent the future generations for their well-being, at least leave sources equivalent. One of the implications of this is that the value of the capital stock, that is natural plus physical capital, should not decline. Individual components of the aggregate could decline in value as long as other components were increased in value, normally through investment, sufficiently to leave the aggregate value unchanged. Number two, strong sustainability. It means that the value of the remaining stock of natural capital should not decrease. It puts emphasis on preserving natural capital under the assumption that natural and physical offer limited substitution possibilities. This definition retains the focus of the previous definition on preserving value and on preserving an aggregate of natural capital. Number three, environmental sustainability. According to this definition, the physical flows of individual resources should be maintained not merely the value of the aggregate. For example, in case of fishery, it emphasizes maintaining a constant fish catch, a sustainable yield, rather than a constant value of the fishery. For a wetland, it involves preserving specific ecological functions, not merely their aggregate value. According to the theorem presented by Hartwig, if all of the scarcity rent from the use of scarce resources is invested in capital, the resulting allocation will satisfy the first definition of sustainability. In general, not all efficient allocations are sustainable and not all sustainable allocations efficient. Furthermore, market allocations can be number 1 efficient but not sustainable, number 2 sustainable but not efficient, number 3 inefficient and unsustainable, and number 4 efficient and sustainable. One class of situations known as win-win situation provides an opportunity to increase simultaneously the welfare of both current and future generations. Thank you.